Hello, my name is Javier Turek. I'm from Intel Labs, and today I'm going to talk about how to achieve slower information decay in LSTMs. This work is a joint work with the Honey Lab in Johns Hopkins University. In order to understand why we want to learn long-range dependencies in sequential data, let's look at the following example. I have the sentence, did the dog, and I want to complete it. Now, if I give you some context and I tell you about, we are talking about the Dino, the family dog, in this case, we'll probably fill in the sentence with did the dog jump or did the dog wag its tail. Now, if I tell you that we are talking about the Pets movie, we may switch to a different option here, which is did the dog talk? To learn long-range dependencies in sequential data, one of the common recurrent neural networks used is the long short-term memory, or LSTM. The LSTM has a cell state, CT in this case, that maintains the information, and we have a forget gate that allows to remove information from the previous cell state time step, and we have the input gate that allows to introduce new information to the cell state or memory. On the right side, we have the formula of the cell state update, and Mato and co-authors and Olivier and Talek also show that if we do a free input regime analysis where we nullify the input and the information leakage on the LSTM, we reduce the formulas and we obtain that the cell state formula over time decays an exponential function. And in particular, that exponential is controlled by the forget gate bias. Olivier and Talek further show that in order to capture very long-range dependencies, we'll need to set the forget gate bias really high. And they propose a way to initialize it. Here we propose an alternative, which is a forget gate that will allow us to have slower information decay. In particular, we propose a power law decay instead of an exponential. The power law has a much stronger decay or faster decay at the beginning, but it has a much heavier tail and will allow us to keep information for longer in the cell state, as shown in the plot. Now, in order to implement this forget gate that has a power law decay, we need a few things. The first thing is we will need the time step t as an input to the network. We are going to process the time step t. We'll need to keep track of a time reference, and we will need to update it once we want to forget things. And also, the power parameter p will allow us to have a slower decay if we have a smaller value. We show a diagram of the power law LSTM where on the left is the specific forget gate, and on the right we can see that the network now has as input the time step t as well as the usual input, and we also have the time reference as part of the recurrency. When we look at the results in the copy task for 200 elements and 1000 elements, we see that the LSTM struggles much more than the other methods to learn to solve this task. On the other hand, the LSTM with the cron initialization is capable of solving the task perfectly, similarly to the PLSTM. However, the PLSTM does not require information on the length of the sequence like the cron initialization. Therefore, the PLSTM learns the long-range dependencies without prior information. We also show in an ablation experiment that the PLSTM learns sparser representations and adapts the decay to the data, which means that if you look at the top plot on the right, you can see only a few elements being active over time. Those are the horizontal strips. For those elements that are active, we see that the values of P are in the or closer to 0, which is lower information decay. And when we try this with language, we show in the sentiment classification on the IMDb dataset that the PLSTM has better performance, in particular for longer sequences. To conclude, we've seen that the LSTM memory has an exponential decay. Therefore, we introduce the power law-based LSTM that has a slower information decay. We also show that it doesn't need to know the maximum length a priori, and it can also learn long-range dependency. Thank you, and happy to answer any of your questions.